We now determine the point on the line y equals 3x plus 5, which is closest to the origin. And this is one of the application of maxima and minima type of problems, or it's otherwise optimization problem. So to solve this type of problems, we'll be utilizing the strategy which I have outlined over here. So we have about 4 steps. In the first step, we draw the picture, and in the second step, we identify the quantity that has to be maximized or minimized, and we write a formula for it. This is basically the objective function. And in the third step, we determine the constraints, or we use the given constraint, rewrite the objective function as a function of only one variable. This is an important step in solving this type of problems. After we figured out the objective function, we have to ensure that using the constraints, we have to make sure that it is written as just one variable. And finally, we use the calculus to maximize or minimize the objective function. Let's now do each steps one by one. So in the first step, we have to draw a picture. As you can see here, I have drawn the picture of this line y equal to 3x plus 5 on the coordinate axis. So this is the line which is y equal to 3x plus 5. So as you can see that it is in the form of ax plus b, where b represents the slope, the y-intercept. So therefore, the y-intercept is 5, which I have marked over here. And this line may have some x-intercept. So that's why I have drawn it like this. It is making some x-intercept over here. That's not an important thing, so we can just ignore it. The important thing is that we need to find the point. The point could be anywhere here. It could be anywhere here, like this, or like this. So considering any arbitrary point, we have to find its distance, which is the shortest distance from the origin. So if I can join this as a line like this, this is the distance. Just looking at the graph itself, we can see that this distance seems to be larger. Suppose if the point was over here, maybe the distance, we can say that this distance between this point and the origin seems to be a little bit closer, or it is minimum when compared to this distance. As well as we can also draw a line like this joining the origin as well as the arbitrary point. In such a case, this distance seems to be minimum. So we are not very sure just by looking at this after we drawn the picture. So we definitely have to use the calculus method, so that will give us a clear picture of which is the exact point on the line which is closest to the origin. And this means we have just completed the step one, that is, we have drawn the picture and understood what's actually going on over here. Now let's move on to the second step. In the second step, we have to identify the quantity which is to be maximized or minimized. As we can clearly understand that we have to find a point which is closest to the origin. So basically, we're talking about the distance. So which means the quantity is distance. Distance is the quantity which we have to minimize. So we have to write a function for the distance. So therefore we can say that the objective function is distance, or we can say it is the distance function. So we have identified the objective function. Now let's move on to the third step. The third step, using the given constraints, we have to rewrite the objective function as a function of only one variable. So first, going back to the second step, let's try to write down the distance function. So distance, we can write down this as d. This is equal to, so it's basically the distance between the origin as well as any point on the line. As we have mentioned that any point on the line is considered as x comma y, so we can use the distance formula. That is, the square root of distance between any 2 point formula is x1 minus x2 quantity square plus y1 minus y2 quantity square. So in this case, we can consider x comma y as a x1 y1 and the origin as x2 comma y2. So when I do that, I'll be getting x minus 0 quantity square plus y minus 0 quantity square. So this is the distance. Let's get this simplified. So you can write down this as d equals quantity square root of x squared plus y squared. So this is basically the objective function or the distance function. In fact, we can write down this as a function notation, that is d of x equals x squared plus y squared. Now moving on to the third step, we have to use the constraint and rewrite this objective function as a function of only one variable. The constraint that is given to us is this equation, that is the equation of the line itself. As you can figure it out here, this equation involves two variables, x and y variable. So we have to convert this into just one variable. So what I can do here is I can write down this d of x. This is equal to x squared plus I'm going to replace y as 2x plus 3x plus y. So when I do that, I'll be getting like this: 3x plus 5 quantity square. This is another root, which can be further simplified as x squared plus we can expand this using the algebraic identity: a plus b quantity square equals a squared plus b squared plus 2ab. So in this case, 3x is the a and 5 is the b. So when I use this identity, I can write down this as 3x quantity square plus b is 5, so it is 5 square, and 2 times of ab, that is 2 times of a is 3x and b is 5. So it comes out like this, everything under the square root. So we'll just simplify this. So this is equal to x squared plus 3x quantity square is 9x squared, 5 squared is 25, and this is a product of 2 and 3x and 5, which gives us 30x. Now we can simplify this further by combining the like terms. X squared and 9x squared are like terms, so when we add these two, we get 10x squared, and then I put this x term with the coefficient 30, that is 30x plus 25. So this is the d of x function, which is basically the distance function. So we have completed the third step as well, which means we have identified the constraint as well as we have written the objective function as a function of just only one variable. Now let's use the calculus, which is the fourth step, to minimize this distance. So let's get back to our distance function. One thing which I'm going to do is I'm going to square both sides, because this is under the square root. To minimize the calculation, we can do the square on both sides. So squaring both sides, I will get d of x quantity squared this side is equal to this side, the square root will go off, so therefore this becomes 10x squared plus 30x plus 25. And this quantity, I can simply write down this as, instead of having it as a square, I can write down this as just a function. So let me call this as a big D of x. It's almost equal to the distance function. So this is the one which we are going to minimize. 10x squared plus 30x plus 25. This is our modified distance function. Now, in the first step of the calculus, we have to set up d prime of x equal to 0 and find the critical points. That is, we find the first derivative of the function which has to be minimized. In this case, it is our distance function. It's actually the square of the distance function. So let's find the derivative of this distance function. So this gives us, we can have to differentiate all the terms on the right side. So let me differentiate each term one by one. Differentiation of 10x squared is, this side it becomes a d prime of x. This is equal to 20 times of x after I apply the power rule, plus differentiation of 30x is 30 times, or differentiation of x is 1. So this is 30 times of 1 is 30, and 25 is a constant, so differentiation of constant is 0. So basically this comes out to be 20x plus 35. Now we have to set this equal to 0. So when I set this equal to 0, I have to determine the value of x. So therefore x cube is equal to negative 30 divided by 20. And subtract 30 on both sides and divide by 20. So when I simplify this, I get the value of x equals negative 1.5. So this is the critical point where the function could be maximum or minimum. So this next step, we had to identify whether this critical point, that is this value of x, it gives the maximum or minimum value. For that, we need to find the second derivative and substitute this x into this one. So let me find the second derivative of the d prime of x, or the d of x. I differentiate this d prime of x one time. That is, I get a d double prime of x on the left side. This is equal to, I have to differentiate this 20x plus 30. When I do that, I get just 20, because differentiation of x is 1. So, and the differentiation of 30 is a constant, which is 0. So this becomes just 20. So this is less than 0, which means when the second derivative is less than 0, we know from calculus it is a point of minimum. And we have no way that we can plug in this into this. It is independent of x. So this point is point of minimum. That is, at x equal to negative 1.5, the distance is minimum. Now to find the coordinate of the point on the line which is closest to the origin, all that we have to do is we just have to substitute this value of x into our line equation, that is y equals 3x plus 5. So we plug in this value of x into this so that we get the exact coordinate on the line. So when I plug in x equal to minus 1.5, I get 3 times of minus 1.5 plus 5, which is minus 4.5 plus 5. This is equal to 0.5, just positive 0.5. So therefore we can say that the coordinate is x comma y, and this is equal to negative 1.5 comma 5, zero point 0.5. Negative 1.5 comma zero point 0.5. So this is the coordinate on the line which is closest to the origin. Maybe we can go back to this line and mark this point. So this is somewhere over here. This is negative 1.5, and maybe this is 0.5. So this point is negative 1.5, 0.5. So when we construct a line to this origin, this is the distance which is minimum of all the points which are on the line. So you can say that the coordinate is minus 1.5 comma 0.5.